So now let's take a look at the effects of some of the kinds of transformations of functions that you've looked at in the past. So suppose, for example, we have the function f of x is equal to x squared, and we will say, well, what happens if we replace f of x equals x squared with f of x plus h? And looks like something like this. So as h is increasingly positive, this new function slides to the left of the original function. When h is negative, it slides to the right. So when h is negative 5, for example, what this means is that if we take a point on the original function, let's say the point 2, 4, well, now when we look at a point on the new function, we can see that unlike in the original function, it's no longer a case that y is equal to x squared. What's true is that y is equal to this new x minus 5 squared. And so that's why this moves to the right. Basically, we're saying that this y value corresponds to this x value from the original function. And so we have to subtract 7 to get back to the x value that corresponds with this 4. So that's why when we have h is equal to negative 5, we're actually moving the function to the right. When h is equal to a positive number, we're moving the function to the left. And this is true whether we're talking about f of x is equal to x squared, or we're talking about square root of x, or we're talking about absolute value of x, or we're talking about exponent function. It works exactly the same way. It just slides the function left to right depending on that value of h. So now what happens if we replace our function? Let's say we'll go back to x squared, and we'll say what happens if we replace f of x with f of x plus k, where k is some number. So instead of having f of x is equal to x squared, we have, let's say, f of x is equal to x squared plus 2. And not surprisingly, what this does is it just takes the original function and slides it k units to the up if k is positive, and down if k is negative. And what we're saying is that instead of f of x being equal to x squared, we're saying that f of x is equal to x squared, but then we add 2 more. So instead of the 0.24, we have the 0.26, because we've added a value of 2 to the 4, so that now our coordinates on the new function are 2, 6. Again, this works with any of our functions, just slides them up k units. And now let's take a look at what happens if, let's go back to x squared, and what happens if we have, now instead of adding, we're multiplying. And if we're multiplying inside the function, so we're saying instead of f of x, we're saying f of, let's say, 2x. So in this case, what we're now saying is that you can see the new function as a is positive and above 1, our new function is getting narrower and narrower. So what that means is that instead of f of x being equal to x squared, we're saying that our value of y is equal not to x squared, but to, in this case, 2 times x squared. So that means we have to move back to a value of 1 to get a value that corresponds to a y value of 4. What happens as as a moves less than 1 but greater than 0, the function is wider, and then when a is, in this case, negative, does the same thing, but if we had, let's say, n equals 3, then we would have had the function operating the reverse way. So we would have had it going from upper left to lower right instead of lower left to upper right. And we can take a look at our other functions. So here, when a is negative, it swings this function around to the left side. For our, let's say, our exponential function, when a is positive, it just narrows it. When a is less than 1, it broadens it. And when a is negative, it just spins it across the y-axis. and that's going to be true with our log functions as well. And with the sine function, what you're seeing is it's changing the period. And so when a is, let's say, positive and greater than 1, the period of the function is getting smaller, so the function is narrower. And when a is between 0 and 1, the function is broader. And when a is negative, again, it just sort of spins it, but it has the same effect on the period depending on the absolute value of a. And then we also can multiply outside the function. And what that does, not surprisingly, is, let's say for f of x equals x cubed, when we multiply the whole thing, all we're doing is we're multiplying the y value by whatever this value of b is. So if we originally had a 0.11, under our new function, 3 times x cubed, instead of 1, 1, we have 1, 3, where the 3 is just 3 times the 1. And again, that's going to work the same way for any of our functions. It just stretches them vertically. And again, it works the same with the sine function. Now, these obviously can all be combined in a lot of different ways. We've looked at 4 different transformations. We could apply all 4 of them to a given function, but let's look at an example here where we're applying just multiplying inside the function and adding inside the function. And one of the things to look out for here is that, let's say when a is 2. Now before, what we were saying was that when h is positive, the function slides to the left just by h units. But notice now that if I start at h is 0, when I make h equal to 2, the function has not slid to the left 2 units, it's slid to the left 1 unit. And the reason is, the way we really should think about this is, because this value a is no longer equal to 1, we can think about this 2x plus 2 cubed as 2 times, and then in parentheses, x plus this 2 divided by 2, or really x plus 1. And so what that means is that the function just slides to the left 1 unit instead of 2. Similarly, when a is negative, now even though when we were making h positive it was sliding our function to the left, when a is negative, this h value is sliding our function to the right. And again, it's because if we factor out the negative 1, then this value inside here, which is 3 over negative 1, is actually negative now. And so as we increase it, the function slides to the right, as was the case when a was positive. And again, this will work the same for all of our functions.